It seems like AI is everywhere these days, right? You can't go a day without hearing about some crazy new thing you can do.
It really is remarkable.
But it makes you wonder, like all this AI stuff, this intelligence, where is it actually happening?
Right, exactly. It's easy to get caught up in the software side, the algorithms and all.
Yeah, the code, the models, all that. But what about the hardware?
The hardware.
Yeah.
That's where the rubber meets the road.
Exactly. And today we're diving into this really cool area where AI meets some pretty powerful hardware.
Field programmable gate arrays.
FPGAs. So for our listeners, maybe you've heard the term, maybe not. What exactly are FPGAs?
Okay, imagine like a computer chip, but way more flexible. With a regular chip, it's designed for one specific task. Once it's made, that's it. Can't change.
It's suck, right? Like it can only do that one thing.
Right. But an FPGA, oh, it's different. Its circuitry, its wiring can be reconfigured after it's manufactured.
Whoa. So after it's already made, you can change how it works.
Exactly. And that is a game changer for AI because AI often needs to do a ton of things at the same time. We call that parallel processing.
And it needs to do them fast.
Ultra fast.
Yes.
Low latency, that's the term.
Right, low latency. So FPGAs can be tailored to fit whatever crazy AI task we throw at them.
You got it. Think of it like having a toolbox where the tools can reshape themselves to fit whatever job you need to do. Pretty cool, huh?
It is, actually. And it's not just theoretical. We're seeing this AI FPGA partnership in so many industries now. We dug through a ton of research for this deep dive, industry reports, all that.
Trying to separate the hype from the reality.
Exactly. And what's wild is that AI isn't just running on FPGAs to make things faster.
No, not at all.
It's actually helping us build and design the FPGAs themselves.
Kind of mind-blowing, right? The AI is helping build better AI.
It's bootstrapping itself. So that's what we're going to unpack in this deep dive. First, how AI is optimizing FPGA design.
Streamlining that whole process.
Then we'll explore how those AI-powered FPGAs are being used in all these different fields.
The applications are just exploding.
Okay, so let's start with that first part, AI for FPGA design. Traditionally, this has been a really complex, iterative process.
Trial and error.
Right. You have all these resources inside an FPGA, memory blocks called block RAM.
Digital signal processors, DSPs for handling all sorts of signals.
And these logic building blocks called flip-flops and LUTs.
Look up tables, LUTs.
Okay. And figuring out how many of each you need, how to connect them all, yeah, that's not easy.
No, and then there's this step called synthesis.
Synthesis, yeah.
You basically take the blueprint of the hardware design and translate it into the actual physical connections on the FPGA.
Got it.
And traditionally, you'd go through this loop, write the design, run synthesis, see how many resources it uses, tweak the design, run it again, repeat, repeat, repeat.
Ugh, sounds tedious.
It could be, but now machine learning is changing the game.
Ah, here comes the AI.
Exactly. We're now training ML models to predict pretty accurately how many resources a design will use before you even go through that whole synthesis step.
Whoa, so you can know early on if you're on the right track.
Much faster design cycles, way less wasted time.
So we're talking about different machine learning techniques, right? The research mentions things like regression and neural networks. Can you give us some specific examples?
Yeah, so one cool example is UTIL-ML.
UTIL-ML.
They use a specific type of neural network called an LSTM.
An LSTM, long short-term memory.
You got it. They're really good at finding patterns in sequential data. And in this case, the LSTM learns to predict how much of the FPGA's processing power a given design will use. And it's insightful because it compares that prediction against the user's target. Like, how much processing power do they actually need?
So it's not just a blind prediction. It's giving you feedback, like, are you close to where you need to be?
Right, exactly. It gives you more information early on to make decisions.
That makes a lot of sense. And then there's Leaper, right? Which uses this idea of transfer learning.
Ah, yes, transfer learning.
Which, can you remind us what that is again?
Sure. It's like, say you learn to ride a bicycle.
Okay.
A lot of that skill transfers over when you learn to ride a motorcycle, right?
I guess so, yeah.
Same basic concept, but applied to AI. In Leaper, they train an AI model on a bunch of data from designing for like simpler FPGAs, less powerful, lower-end environments.
Okay.
And then they use that knowledge to predict how the design would perform on much more powerful, high-end FPGAs, like the ones you'd find in the cloud.
Clever.
It is, right. Because it's so much faster than having to generate training data from scratch for every single high-end FPGA.
So it's a shortcut. But a smart one.
Exactly. You're leveraging existing knowledge.
Very efficient. Okay, and then there's this tool called Rule 4 LALY, which sounds particularly relevant for, specifically for AI on FPGAs.
Oh, Rule 4 Millimeter is really interesting. It's open source, by the way. And it uses these trained regression models, similar to what we were talking about, to predict resource usage before synthesis.
Oh.
But what's really cool about it is it doesn't just tell you how much memory or processing power you'll need overall. It actually estimates how long it will take for a specific neural network to run on the FPGA.
Wow, really?
Yeah. And it takes into account the actual architecture of the neural network, like how many layers it has, what types of layers, and uses that to predict the performance.
So if I'm designing an AI application for an FPGA, this tells me early on if my chosen neural network will even work well on that hardware.
That's exactly the point. You can test out different neural networks, see which ones fit best, all before you go through the whole design process.
Amazing. Okay, so we've talked about resources. But once you know how many of each you need, you have to figure out where they go on the actual chip. Placement, and then how to connect everything. Routing. And I imagine this also has a huge impact on how well the FPGA performs.
Oh, massive impact. The physical layout, the connections, it all affects the speed, the efficiency, everything. Longer wires means slower signals.
The traffic jams, essentially.
Exactly. Congestion, that's what we call it. And these have always been incredibly difficult problems to solve. A lot of manual work, a lot of back and forth.
But surely AI can help here too, right?
Oh, you bet. And one approach that's gaining traction is reinforcement learning.
Reinforcement learning. We talked about that a bit in our episode on robotics.
That's right.
It's where the AI learns through trial and error, right?
Yeah, it's kind of like teaching a dog tricks with treats. You reward the behavior you want, and over time, it learns to do the right thing.
Got it. So how is that being applied to placement on an FPGA?
Well, there's this project called RLPlace.
RLPlace.
And what they do is they create this reinforcement learning agent, and its job is to figure out the best locations for all the different components on the FPGA.
So it's like the FPGA is a giant puzzle board, and the AI is trying to figure out where all the pieces go.
That's a great analogy. And the reward it gets is based on how short it can make the total length of all the wires.
Interesting. So shorter wires mean faster signals, which means a better performing FPGA.
You got it. And the AI, over time, learns which placement strategies lead to the shortest wires.
Cool. So that's placement. But what about that congestion problem we talked about, making sure the routing doesn't get all jammed up?
Ah, yes, congestion. That's critical. And machine learning is helping here as well. There's a tool called MLCong, for example, that uses a statistical technique called linear regression.
Linear regression.
Yep. It looks at factors like the total wire length in a certain area, the density of connections, and a measure of how routable that area is.
Okay.
And based on all that, it predicts where congestion might occur during placement.
So it's like a traffic forecast for the FPGA.
Exactly. And then there are more advanced techniques like DLCong, which use deep learning, specifically a type of neural network called a convolutional encoder-decoder.
Okay. Getting a bit technical here.
Well, the main point is these deep learning models can learn even more complex patterns in the data.
Got it.
And they can predict congestion across the whole chip with even greater accuracy.
So you can catch those potential bottlenecks early on.
Precisely. Early detection is key. And then there's this other tool called ML Select, which is interesting because it takes a higher level view.
What do you mean?
Well, instead of optimizing individual placement decisions, it recommends the best overall placement flow.
The flow.
Right. The sequence of steps, the specific techniques to use, all with the goal of minimizing the final wire length after everything's routed.
Oh, I see. So it's not just about the individual decisions, it's about the strategy.
Exactly. Having an AI guide for the entire placement process.
Wow. Okay, so AI is optimizing placement, it's predicting congestion. We've covered performance. But what about power consumption?
Ah, yes, power. That's a big one, especially for devices that need to run on batteries or anything that's energy sensitive.
Right, like wearables, edge devices, all that.
Exactly. And thankfully, AI is proving incredibly useful here too.
So how are they tackling this? How are they using AI to optimize power consumption on FPGAs?
Well, one really effective method is ensemble machine learning.
Ensemble machine learning. Sounds fancy.
It's basically combining the predictions of multiple different machine learning models. So instead of just using one model, use several and combine their results.
Okay, and why is that better?
It often gives you more robust, more accurate predictions.
Makes sense.
And in this case, these ensemble models can look at all sorts of information about the application running on the FPGA.
Okay.
The software code, the hardware behavior, all sorts of stuff. And from that, they can predict how much power the application will actually use.
I'll add it.
And once you have those predictions, you can start doing some really clever power management. Well, one technique is called dynamic voltage and frequency scaling.
DVFS?
Yep. It's basically adjusting the voltage and the clock speed of different parts of the FPGA on the fly based on what's happening.
So if a part of the FPGA isn't being used heavily, you can slow it down, lower the voltage, save some power.
Exactly. You only use the power you need when you need it. Another technique is clock gating.
Clock gating?
Yeah. So every part of an FPGA has a clock signal that keeps it running. But if a part isn't being used, you can actually turn off its clock.
And that saves power.
Absolutely. And AI predictions can help determine when and where it's safe to do that.
Smart. And the research mentioned a really interesting case study from high-energy physics.
Oh, yeah, that was a cool one. So in particle physics, they use FPGAs to process the data from these huge particle detectors.
Okay.
And these detectors generate massive amounts of data, and they need to process it really, really fast.
High throughput, low latency, all that.
Exactly. And what they did was they used machine learning to optimize how these particle tracking algorithms were implemented on the FPGAs.
Wow. And
not only did they get amazing performance, but they were able to do it using way less power than if they had used traditional GPUs.
So real-world proof that AI can help squeeze more performance out of FPGAs while using less energy.
Absolutely. Really impressive stuff.
So we've seen how AI is revolutionizing the way FPGAs are designed. But now let's switch gears and talk about AI actually running on these FPGAs.
Right, the other side of the coin.
And the research highlighted some really fascinating industry-specific applications.
Yeah, a lot of diverse areas.
Let's start with automotive. The automotive industry is going through such a massive transformation right now.
Oh, it's a whole new world. Autonomous driving, electric vehicles, the connected car.
And FPGAs are playing a key role, right?
Absolutely. They're becoming essential in all sorts of systems within the car.
Like, give us some examples.
Okay, so think about advanced driver assistance systems. Right, ADAS. Things like lane keeping assist, adaptive cruise control, automatic emergency braking.
All those features that are making cars safer.
Exactly. And these systems rely on a ton of sensors, cameras, radar, LiDAR.
Right.
And all that data needs to be processed in real time, and decisions need to be made incredibly quickly.
You can't have any lag when you're talking about safety.
Absolutely, and that's where FPGAs shine. They can handle those massive data streams and provide the ultra-low latency that those safety-critical functions demand.
So the FPGA is like the brain of the ADS.
In a way, yes. And then you have in-vehicle infotainment systems.
Yeah.
Yep, all the navigation, entertainment, communication stuff.
Which is becoming more and more sophisticated.
Oh, absolutely. And as those systems become more complex, they need more processing power.
And low latency, again, for a smooth user experience.
Exactly. No one wants a laggy touchscreen. And then, of course, you have the whole connected car aspect.
V2X, vehicle to everything.
Right, V2X. Cars talking to each other, to the infrastructure, to pedestrians' phones.
So much data flying around.
It's incredible. And all that communication needs to be managed efficiently and securely.
And guess what? FPGAs are great at that too.
They really are. They can handle the high-speed networking, the real-time processing, all of it.
Okay, so FPGAs are clearly a good fit for these advanced automotive systems.
Yeah.
But where does AI come in?
Well, in autonomous vehicles, AI is absolutely essential for things like object detection.
Identifying pedestrians, other cars, obstacles, all that.
Exactly. And FPGAs can run those AI algorithms really, really fast, making sure the car can react quickly to its surroundings.
We sense.
AI on FPGAs is also being used for path planning, figuring out the safest and most efficient route.
Okay.
And even for making those split-second driving decisions.
Wow. So AI is basically doing the driving, and the FPGA is providing the hardware platform.
You got it. And it's not just about the core driving functions. We're also seeing AI on FPGAs being used for things like driver monitoring.
So like making sure the driver isn't falling asleep or getting distracted.
Exactly. It can analyze driver behavior and provide alerts if needed. And it can also be used to improve voice control systems, making them more responsive and intuitive.
Makes sense. What about other applications in cars?
Well, AI-powered FPGAs are also being explored for things like predictive maintenance.
So like anticipating potential problems before they happen.
Exactly. By analyzing sensor data and using AI algorithms, the car can predict when certain components might fail and alert the driver to get them checked.
That could save a lot of headaches.
Absolutely. And it can also be used for advanced battery management in electric vehicles.
Oh, that's important.
Absolutely. AI can optimize charging and discharging cycles, maximizing battery life and range.
So AI on FPGAs is really touching every aspect of the modern car.
It is. It's driving innovation across the board, literally.
Okay, let's move on to another industry with demanding requirements. Aerospace and defense.
Aerospace and defense, yeah. Reliability is paramount in that world.
Absolutely. Mission-critical applications.
Mm-hmm.
And FPGAs have a long history in this space, right?
Yeah. Oh, yeah. They've been workhorses for decades. You find them in radar systems, in signal processing units, in communication systems for aircraft and satellites, even in unmanned aerial vehicles.
UAVs, drones.
Exactly. And the reason they're so popular is because they're really good at handling complex tasks. They can operate in extreme environments, and they have long life cycles.
Which is important when you're talking about things that need to be reliable for years.
Absolutely. And now the integration of AI is opening up even more possibilities.
So give us some specific examples of how AI on FPGAs is being used in aerospace and defense.
Okay, so think about a military radar system.
Okay.
It needs to be able to detect and classify targets really quickly and accurately.
Right.
And AI algorithms running on FPGAs can analyze those radar signals much faster and with greater precision than traditional methods.
So it's like having a super-powered radar operator.
In a way, yes. And in satellites, which are constantly bombarded by radiation, FPGAs are used for all sorts of critical data handling tasks. And AI can help optimize how that data is processed and managed, even making decisions about what data to keep and what to transmit back to Earth.
Wow, so AI is helping satellites make better use of their limited resources.
Exactly. It's like having an intelligent assistant on board. And then in search and rescue operations, AI-enhanced FPGA systems are improving communication and tracking capabilities.
So they can find people faster and more accurately.
Exactly. And in UAVs, drones, AI on FPGAs is enabling more autonomous flight, real-time object recognition, and even coordinated swarming behaviors.
So the drones can fly themselves, identify targets, and work together as a team.
Pretty much. And one thing that's really important in aerospace and defense is redundancy.
Redundancy.
Yeah, making sure critical systems have backups. Like, if one system fails, there's another one ready to take over.
Makes sense. Can't have a single point of failure.
Right. And one common technique is triple modular redundancy.
Triple modular redundancy.
Yeah, basically you have 3 identical systems running in parallel. And if one of them produces a different result than the other 2, you know something's wrong.
So it's like a voting system, the majority rules.
Exactly. And that's often implemented using FPGAs because they can be configured to provide that level of redundancy.
So they're reliable, they're powerful, and they can even have built-in backups.
FPGAs are really the workhorses of aerospace and defense.
Okay, let's move on to telecommunications.
Yeah.
Another industry that's all about moving massive amounts of data around.
Telecommunications, yeah, the backbone of our digital world.
And FPGAs are key components in that infrastructure, right?
Oh, absolutely. You find them in all sorts of network equipment, from high-speed switches and routers to cybersecurity appliances.
Okay.
And with the rollout of 5G and the rise of things like the Internet of Things, the demands on those networks are just exploding.
More devices, more data, higher speeds.
Exactly. And FPGAs are uniquely suited to handle that. They can process data in real time, manage high-speed connections, and adapt to changing network conditions.
So they're really flexible and adaptable.
Extremely. And the integration of AI is taking things to the next level.
So how are they using AI on FPGAs in the telecom space?
Well, one big application is deep packet inspection for network security.
Deep packet inspection.
Yeah, it's basically analyzing the data packets that are flowing through the network.
Okay.
And AI algorithms running on FPGAs can identify patterns in that data that might indicate malicious activity.
So they can spot viruses, malware, hackers, all that stuff.
Exactly. And they can do it at incredibly high speeds so it doesn't slow down the network.
Makes sense.
FPGAs are also being used to accelerate AI inference for various telecom applications.
AI inference, that's using a trained AI model to make predictions, right?
That's right. So things like natural language processing for chatbots, personalized recommendations, all that.
Okay.
FPGAs can make those AI models run much faster, which improves the user experience.
Got it.
And we're even seeing the emergence of system-on-chip FPGAs. Yeah. These are basically chips that combine a traditional processor with the programmable logic of an FPGA.
Okay.
And this allows you to implement AI algorithms directly on the chip, which is super efficient and low power.
Makes sense.
And there's some really interesting research going on right now looking at using FPGAs as AI network interface cards.
AI NICs?
Yeah. These are basically specialized cards that handle the communication between servers in a data center.
Okay.
And by using FPGAs for this, they can reduce delays and congestion, which is really important for large AI workloads.
So they're like traffic cops for the data center.
You could say that.
Yeah.
And the report specifically mentioned Myrtle.ai. They're a company that makes AI solutions for the telecom industry.
Okay.
And they use Altera Agilex 7 FPGAs in their Valo platform.
And why those specific FPGAs?
Well, they're known for their low latency, which is super important for things like high-frequency trading, wireless communication, and cybersecurity.
It sounds like FPGAs are really essential for keeping up with the ever-increasing demands on our networks.
Absolutely. They're the unsung heroes of the telecom world.
Okay, finally, let's talk about data centers. These massive facilities are the engines of the internet, processing and storing unimaginable amounts of information.
Yeah, data centers are the foundation of the cloud.
And we're seeing more and more FPGAs being used in data centers.
Well, absolutely. They're being used to accelerate all sorts of workloads, from AI inference to database management to high-performance computing.
Okay.
And the reason they're so attractive is because they're really good at handling parallel tasks. They can be customized for specific workloads, and they're very energy efficient.
Great.
And the integration of AI is only making them more powerful.
So give us some examples of AI-driven applications on FPGAs in data centers.
Okay, so one of the biggest use cases is accelerating AI inference.
AI inference, again, that's running a trained AI model to make predictions, right?
Right, so things like natural language processing, image recognition, recommendation systems. And FPGAs can make those models run much faster, which is crucial for providing a good user experience.
Makes sense.
They're also being used to speed up other demanding workloads like database management, genomics research, and network security.
So basically anything that requires a lot of processing power.
Exactly. And they're also good at handling what we call high-performance computing applications.
Like scientific simulations, financial modeling, that sort of thing.
Exactly. And because FPGAs can process so much data in parallel, they can handle a huge number of users or requests at the same time.
So they're really good for cloud-based services.
Absolutely. And while GPUs have traditionally been the go-to for training AI models, FPGAs are starting to make inroads there as well.
Oh, really?
Yeah. They can be used to create these custom hardware pipelines that are optimized for specific parts of the training process.
Interesting.
And they can also help improve things like data input and output, which is a big bottleneck in many data centers.
So they're becoming more versatile.
Definitely. They're finding their way into more and more applications.
So across all these different industries, we're seeing a similar story. FPGAs providing the speed, the flexibility, the efficiency that AI needs, and AI, in turn, helping to design and optimize those FPGAs.
It's a really powerful synergy.
It is. Now, the research also highlighted some pretty cool AI-powered tools and methodologies that are making FPGA development more accessible.
Yes, this is a big deal. Because traditionally, programming FPGAs has been pretty challenging.
Yeah, it's not exactly something you learn in a weekend coding boot camp.
Not quite. You usually need to learn a hardware description language like VHDL or Verilog.
Okay.
And those languages are pretty different from the software languages that most people are familiar with.
So it's a steep learning curve.
It can be. But now we're seeing a shift towards more user-friendly tools and approaches.
Like what?
Well, one big one is high-level synthesis.
HLS.
Yep. And with HLS, you can describe the behavior of your FPGA design using more familiar languages like C or C++A.
So you don't have to learn a whole new language.
Yeah, exactly. The HLS tool takes care of translating your code into the low-level details that the FPGA needs.
That's awesome.
It is. It makes FPGA development much more accessible to a wider range of engineers.
And the big FPGA vendors are also providing AI-specific tools, right?
Absolutely. Xilinx has Vitis AI, which includes pre-optimized AI models, libraries, and tools for things like quantization.
Quantization.
Yeah, it's a technique for reducing the precision of numbers in a neural network.
Great.
It can make the models smaller and faster without sacrificing too much accuracy.
Interesting.
And Intel has the Intel FPGA AI suite, which integrates with their OpenVino toolkit.
OpenVino.
Yep. And that allows you to convert AI models that were trained in popular frameworks like TensorFlow and PyTorch so they can run on Intel FPGAs.
So it's making it easier to deploy AI models on FPGAs.
Exactly. And all these tools are really helpful for both experienced FPGA developers and people who are just getting started.
And it's not just the big companies, right? The open source community is also contributing some really cool stuff.
Oh, the open source community is amazing. They're constantly pushing the boundaries.
Give us some examples.
Okay, so there's HLS4ML.
HLS4ML.
Yeah, it's an open source tool that can translate machine learning models from Python libraries like Keras and PyTorch into HLS code.
So you can take your existing AI models and deploy them on FPGAs really easily.
Exactly. And then there's Rule4MLU, which we talked about earlier for its resource estimation capabilities.
Right, go.
But it's also open source. And then there's SymbiFlow, which is a complete open source tool chain for FPGA development.
A whole tool chain.
Yep. It includes everything you need to design, synthesize, and program FPGAs from multiple different vendors.
Oh, that's impressive.
It is. And having those open source tools is really important because it allows more people to experiment with FPGAs and contribute to the ecosystem.
Absolutely. And it's even getting to the point where AI is being used to help write the hardware code itself.
Oh, yeah, that's wild. Like with Liquid Instruments, Moku Cloud Compile platform, they're using AI tools like ChatGPT to assist with generating VHDL code, which is one of those hardware description languages we talked about.
So the AI is helping to program the FPGAs. That's pretty meta.
It is, and it's just one example of how AI is becoming more and more integrated into the FPGA development process.
Okay, so all these tools and techniques are making FPGA development more accessible. But what are the real benefits we're seeing from this deeper integration of AI and FPGAs?
Well, the benefits are huge. We're seeing significant performance improvements, especially for AI workloads.
Faster processing, lower latency.
Exactly. And that's because FPGAs are really good at parallel processing, which is what AI often needs.
Right.
And they're also very energy efficient, which is becoming increasingly important as we deploy more and more AI at the edge.
Edge computing, that's basically processing data closer to where it's generated, right?
Right. Instead of sending everything to the cloud, you can do some of the processing locally on devices at the edge.
Okay.
And FPGAs are ideal for that because they're low power and can handle real-time processing.
Makes sense.
And because FPGAs are reconfigurable, you can adapt them to changing AI models and standards.
So they're future-proof, essentially.
In a way, yes. And all these AI-powered tools are making FPGA development much faster and easier.
So shorter development cycles, faster time to market.
Exactly. And in the long run, all this could lead to significant cost savings.
Through lower energy consumption, longer hardware life cycle, all that.
Absolutely. It's a win-win situation.
So it sounds like this marriage of AI and FPGAs is pretty advantageous. But are there still challenges?
Oh, there are always challenges in technology.
Like what?
Well, FPGAs are still relatively complex to program. Even with all these new tools, it takes some expertise.
Right.
And there are still resource limitations.
Meaning?
Well, FPGAs have a finite amount of memory, processing power, and so on.
Okay.
And if you're trying to implement a really large, complex AI model, you might run into those limitations.
I see.
And it can be tricky to find the right balance between performance, power consumption, and resource utilization.
So it's a bit